Have you ever just looked at one of those colossal container ships and thought, how? How on earth does that thing not just tip over? Well, today, we're going to pull back the curtain on the incredible invisible math that keeps our whole world afloat. It's a story of gigantic forces all held in a really delicate balance. Now, really think about it for a second. We are talking about floating skyscrapers, some of them heavier than an entire city block, carrying billions of dollars worth of stuff, all balancing on water, which is, constantly moving. It seems completely impossible. But it's not magic. It's just a brilliant, super high-stakes physics problem that's being solved every single second of every single day. So what it all boils down to is this. Keeping a ship upright is all about managing a giant balancing act on a scale that is just, well, it's hard to even wrap your head around. And to really get this balancing act, we need to meet the two main players in this constant, invisible tug of war. They're always working against each other, and the secret to everything is managing the relationship between them. So let's meet our contenders, gravity and buoyancy. One of them pulls down, the other one pushes up, and somewhere in the middle of that fight lies the secret to staying afloat. So on one side, you've got the relentless downward pull of gravity, acting on every single bit of the ship's weight. And fighting right back is buoyancy. That's the upward force from all the water the ship is pushing out of the way. Now, when a ship is just sitting there nice and stable, those two forces are perfectly balanced. But for that balance to actually work, it's not just about how much force there is, it's about where those forces are pushing and pulling from. Okay, so first up is the center of gravity. You can kind of think of this as the ship's single balance point. Like when you try to balance a pencil on your fingertip, that one little spot where it doesn't fall, that's its center of gravity. And for a ship, that point moves around depending on where you load all the cargo, the fuel, all of it. The force pushing back up acts from the center of buoyancy. That's basically the geometric middle of the part of the ship that's underwater. But, and this is the absolute key, unlike the center of gravity, which is relatively stable, the center of buoyancy moves the instant the ship rolls because the underwater shape changes. And that little shift, well, that's where the magic happens. So picture this. A wave hits the ship and it rolls. That center of buoyancy immediately shifts to the side, right? But the center of gravity kind of stays put. For just a split second, they're not lined up anymore. And that misalignment, it creates this powerful twisting force, like a lever, that literally pulls the ship back upright. That's the righting lever, and it's the secret sauce that keeps these massive vessels from capsizing. So how in the world do sailors manage these incredible forces? Well, they don't guess, not at all. They have a rule book, a manual, just packed with the precise math of stability. And the source for our explainer today is exactly that. This isn't some theoretical, dusty old textbook. No, this is a real-world, practical guide for ship's officers, and it's full of the actual problems and calculations they have to master to keep their ship and their crew safe. Just look at this table of contents. We're talking about dozens of super specific scenarios. How to calculate the ship's list or its trim, what to do when the water density changes, and they even have plans for what happens if the hull gets damaged. The level of detail here is just staggering. And the preface says it all. The whole point is to provide practical problems. This isn't just about passing an exam. This math is a life or death skill, and it's practiced every single day out on the ocean. For these officers, the numbers have to be right. Every single time. All right, so let's see this in action. We'll grab a real scenario straight from the manual. How do officers actually apply all these ideas when things are always changing out at sea? Okay, here's a problem right out of the book. A ship needs to load 130 tons of cargo. We're talking the weight of a huge blue whale. But it has to be placed 2 meters away from the ship's centerline. So, what happens to the balance? A ship's officer isn't just going to eyeball it. Nope. They turn to their stability manual and use a precise formula that looks just like this. Now, don't worry, you don't need to understand all the math here. The important thing is just to see that they are calculating the exact shift in the ship's center of gravity and figuring out exactly how that's going to affect its balance. And this is what's so cool about the math. The result isn't a guess. It's a precise prediction. The ship is going to list or tilt by exactly 1 degree and 30 minutes over to the starboard side. They know what's going to happen before it even happens. Okay, that's pretty amazing. But what about something more complicated? Solid cargo is one thing, but these massive ships are carrying huge amounts of liquid in their tanks. Fuel, fresh water, ballast water for balance. What happens when that stuff starts moving around? Well, this introduces a massive risk. It's called the free surface effect. See, when a tank is only partially full, the liquid inside can slosh back and forth as the ship rolls. And all that movement actually works against the ship's stability. It basically raises the center of gravity and shrinks that all-important righting lever we just talked about. And that is incredibly dangerous.
But you guessed it, this is not left to chance either. The Stability Manual has a whole section just for calculating the free surface correction. Officers have to account for the size, the shape, and how full every single tank is to figure out its exact destabilizing effect and make sure the ship stays safe.
So yeah, these are some seriously complex calculations, but they are not just abstract math problems. They are the invisible bedrock that our entire modern world is built on. Think about it. Every single one of these calculations makes sure the crew on board gets home safe. It protects billions and billions of dollars in cargo, from the car you drive to the phone in your pocket. And ultimately, it's what keeps the entire global supply chain running, the very thing our economy depends on. So, here's the big takeaway. The next time you see one of those ships on the horizon, remember, you're not just looking at a big piece of steel. You're watching a living, breathing physics problem being solved in real time. A massive dynamic balancing act, all managed by the unseen but absolutely essential language of math. And it really makes you wonder, doesn't it? From the bridges we drive across to the airplanes we fly in, what other invisible math is out there quietly holding our world together?